Section 7.1 is graphing systems of equations. So got a little bit of writing to do, notation here. So a system of equations is two or more linear equations. Those are equations that when we graph them make a line. So a system of equations is two or more linear equations, and a solution for the system of equations is any ordered pair that satisfies both equations. That means that makes both equations true. So if it satisfies an equation, it makes it true. Okay? Some more definitions. Why don't you pause and write all this down and then come on back and I will go through it while you're not trying to write while I talk. Okay, two types of graphs. Consistent graphs are graphs that intersect or coincide. That means that they are the same line. Coincide means on top of each other, the same line. So if the graphs intersect or coincide, in other words, if they touch each other in any way, the system is consistent. A system is inconsistent if the graphs are parallel. In other words, if they don't touch. So if the graphs are parallel, the system is inconsistent. Now, if it is consistent, if it touches somewhere, we have two subcategories. The first is that it is independent. So a consistent system that has exactly one solution is said to be independent. So two lines that touch exactly one place is independent and consistent. Dependent, if a consistent system that has an infinite number of solutions is said to be dependent. So two lines that touch, but they are exactly the same. So every point on one line is also a point on the other line, is both consistent and dependent. Let's look at this in another form. Make yourself a table. And then again, come on back. Okay, so intersecting lines. The graph would look something like this. Lines that intersect cross in one place. There is exactly one solution for this graph. There's only one point that is on both of those lines. And therefore we call it consistent and independent. The same line, also called corresponding lines. I'm sorry, coinciding. You got my terminology wrong. The same line is also called a coinciding line. So if I graph one line and then graph another line and it's right on top of it, two lines together, there are infinite solutions. Every point on one graph is a point on the other. We call this consistent and dependent. Parallel lines, two lines that do not touch. There are no points that are solutions for both of the lines. So there are no solutions, and we call it inconsistent. Okay? We'll keep talking about these when we get to class. All right, so a system of equations. We're going to graph the system so that we can see what they look like. So here are my two equations that make up my system. I'm going to graph line number 1, y equals 2x minus 1, using the y-intercept of -1, up 2 and to the right 1. You might want to count a couple slopes so that when you connect your lines, you make sure that you've got a nice straight line. Okay, I'm going to switch colors to do graph number 2. So graph number 2 is going to be green. We go up 5. 1, 2, 3, 4, 5. My slope is down 3. 1, 2, 3 to the right 1. 1, 2, 3 to the right 1. And I'm going to connect those. And you can see that these two graphs have one point of intersection. These are intersecting lines. Oh, goodness. Intersecting. They have one solution. There we go, that's better. Okay, intersecting lines, one solution, which makes them consistent and independent. Okay, and I'm not sure what this solution is. It's hard to tell from the graph, but there is one solution, one point that would make both of those statements true. Let's look at another one. So again, I'm going to graph the lines in two different colors. We'll do the first one in blue. -3 is my y-intercept. My slope is +2. Up 2 and to the right 1, up 2 and to the right 1. So there's the blue line, the first one. Okay, and you really should be using a straight edge to graph these lines. And then we'll use green for the next one. Okay, y equals 2x plus 1, so I go up 1, and now I'm going to count my slope again, up 2 and to the right 1. And I hope you can see that these two lines are parallel. They do have the same slope. The slope of both of these lines is 2. Well, slope is 2 for both. So these are parallel lines. There are no solutions. There's not a single point on the green line that is also on the blue line. No solutions. We call these inconsistent. Okay? Sorry, the pen is not working very well. There we go. Inconsistent. All right, let's try another one. Now, to graph this, I'm going to have to do a little rearranging or find the x and the y-intercepts. So take a minute on your own and take these two equations and rewrite them or fix them so that you can graph them easily. Try that on your own. Okay, I'm going to go ahead and use my equations by adding 3 to both sides, dividing everything by 2. Here I'm going to divide everything by 4 and simplify my slope. And I hope that you can see that these two lines are the exact same line. Even though they looked different up here, once I simplified them, they're the same line. So up 3, slope of up 3 and to the right 2. So that's the first line. It's also the second line. So therefore, and I know it doesn't look like it because I wobbled a little bit, but they lie exactly on top of each other. Those are called coinciding lines. It's just a fancy word to say that they are the same line. There are infinite solutions. Every point on one line is a point on the other line. They are consistent and dependent. Oops, sorry, dependent. Okay, so we've graphed all 3 different kinds of lines to see what kind of a system they form and how many solutions they might have. One of the other things we're going to do is to actually solve the system by graphing. In other words, find the point of intersection. Find the ordered pair. Because again, the solution of a system are any ordered pairs that satisfy both equations. So if I have intersecting lines, I would expect to find one solution, one point where they intersect. If I have parallel lines, I will say there are no solutions. And if I have coinciding lines, the same line on top of itself, then every point on the first line is also a point on the second line. So let's try to graph these. Again, take a moment on your own and graph these two lines and see how you do. Okay, y equals, I'm going to add the 2x to both sides, so I have mx plus b form. And that one's in a good shape. So I'm going to graph this one first. I should use my different colors again, shouldn't I? That's okay. We'll stick with green for the first one. So -4, 1, 2, 3, 4. And the slope is 2. Up 2 and to the right 1. Since I can't use a ruler here on my computer, I'm going to go ahead and count a few more of these slopes just so I have a good sense of where this line is going to be. Every time I just count up 2 and to the right 1. Up 2 and to the right 1. I'm going to draw this line. I'm going to come back with a different color here. Let's see, we'll try purple. And we'll do this one in purple. Y equals -x plus 5. So 1, 2, 3, 4, 5 for my y-intercept. -x, down 1 to the right 1. Down 1 to the right 1. You can see that I have found this point of intersection. So these two lines intersect at the point 3, 2. And if I test this point into both equations, so this is where I'm going to check my work. We'll check the point 3, 2. In the first equation, y minus 2x equals -4. I put in 2 for y and 3 for x. I do, in fact, get -4. My other equation, y equals -x plus 5. If I put 2 in for y and 3 in for x, so -3, that is true as well. So that is the point of intersection. It is also called the solution of the system of equations. And that's it for this.